We are happy to have, okay, we are happy to have Roma Bezrukavnikov from MIT on Springer theory for homogeneous affine Springer fibers. Roma, please.
Okay, thank you very much for the invitation. Okay, so I want to tell some story based on joint work with so my former student Pablo and Michael McBreen. And Zhiwei Yun. And maybe in the end I will mention a forthcoming paper with the same authors, or maybe not. But mostly I'll be talking about existing paper. Okay, so first I want to talk about the background, and I don't assume everybody is at home with Springer theory, although it is so the usual Springer theory. Okay, I will not talk about the theory so as much as about some specific objects. So if G is a semi-simple reductive, sorry, semi-simple algebraic group over C. So we have its Lie algebra. It contains the nilpotent cone, which is a single algebraic variety. And then it has this famous Springer resolution. So this map is resolution of singularities. And this end-field can be described as the cotangent bundle to the flag variety of the algebraic group, G mod B. And it can also be described as a set of pairs. So I think of G mod B as a space of barrels. And X, so X will be in the radical of the barrel. So for
Ron, may I ask you a kind of radical question, since you speak about radicals? So if the speakers will assume that G is a SLN, will they miss?
No, perfectly fine. You can assume,
okay.
Yeah.
So then maybe it can kind of reduce the new list of new words. Okay.
Sure. So we can assume and invited to assume G is a SLN. And then, so G mod B is, of course, the set of flags. Well, they usually write it this way, so it's V1 and V2, so these are linear subspaces. And Vn, which is like, say, C to the n. So this is the it carries a transitive G action, so it's a maximal projective homogeneous space for G. Okay, so and then X will be just a matrix preserving the strictly preserving the flag. So sending the I to the I-1, which certainly implies it's nilpotent. And so let's call this map pi. And the Springer fiber is just fibers of pi are called Springer fibers. Pi itself is a Springer map, or cross-index Springer map. Oh, maybe this one, Springer map, and there's a version of cross-index Springer, it doesn't matter. So Springer fibers. So again, these are parameterized flags resolved by a given matrix. Well, maybe. So I typically write, maybe I'll write this B, and then I'll write BE to be the pi inverse of E. So well, if E is regular, nilpotent, so one Jordan block. then, as everybody can do as an exercise, just a point. And if it's 0, it's of course G mod B. G mod B is B. But if he is subregular, so meaning 2 blocks of sizes 1 and -1, so this is called subregular. So this is a so-called, it's just the BE is the chain of P1s. Maybe without writing it down, I can just say who these P1s are. You can just fix all elements in the flag, and then one will be the freedom that's left for you is that you can choose this one vector space, but it's stuck between vi -1 and vi +1, which are fixed. So you have P1 worth of choices. So this is the way. This is how they intercept. Okay, this is all pretty nice and easy. So geometry of, but okay, so this is maybe misleading. The simple examples in general, components are singular, and singularity are pretty complicated. So there are many geometric questions now. Quite hard. But still there are good things to say about it. And so, but maybe it's worth mentioning that. So geometry of BE, it kind of plays a significant role in geometric representation theory. Okay, so it was studied, and there are different sources of motivation. So an early one, going back to the work of Springer himself, that point counts over FQ, or more generally, or trace of Frobenius. I mean, you can modify this on cohomology of BE. It relates to character values for finite Chevalier groups, green functions. For G of Q. And then this cohomology or K theory, it realizes various representations. I mean, the cohomology is not, let's not go deep into this, but these are very close spaces there, in fact, isomorphic or at least tensor Q. So it carries representations of the Weil group, and then you can modify it to get a fine Weil group, and you get affine Hickey algebra. So that's representations that people are interested in particular interested in local Langlands theory. And then, okay, so maybe this is a minute for self-advertising. So categorifying this, I can say so DB coh of BE. So it has an interesting geometric representation theoretic meaning, has a representation theoretic relevance, and so this is what I called a theory of non-commutative Springer resolution. So it has an interesting T structure whose heart is responsible for various questions in representation theory, but that's not what I want.
Rom, so yeah, I understand it's not topic of your talk, but DB Koch, what do you mean? It has, I understand it has interesting T structures, but when you say non-commutative Springer, you mean categorical resolution? What?
Yes. So N has also a non-commutative resolution in the sense of Vandenberg. So
okay.
And it's derived equivalent to the usual resolution, and then there are various interesting structures which I talk about on another occasion, but that's not.
Okay.
Okay.
Roman, in this case, the DB code on BE, so that Springer resolution is you're resolving what the closure of the orbit.
That is right. That is right. That is right. So I wasn't very precise. What I mean is that so non-commutative Springer resolution is some algebra A, and so dB of A modules is dB coefficient tilde. But then you can specialize it to a central character AE, and it will be dB coefficient. That's what I meant. Because I mean, like, and usually I talking about some representation category, you fix the central character first, and that will be compared to AE. Okay. All right. So fine. Just before passing to the more general story, I want to mention some key features. So BE can be realized. So it sits in an algebraic symplectic manifold as a singular Lagrangian, known as they now call it Lagrangian skeleton. So I want to mention this. So the idea is that, okay, so you're fixing some important element. Of course, it's only important up to conjugacy, so you're really fixing some important orbit. But if you want to focus your attention on the fiber over that, and somehow the natural thing to do is to sort of realize it as a central fiber of some map, not just some arbitrary fiber, and you can do it. It's not so you can choose SE. So this is a transversal slice to an orbit. And then we get like maybe YE would be, so SE is maybe in G, and as I will say in a minute, it can be even chosen to be in a affine linear subspace. And then maybe YE is gonna be N cap plus E, and XE will be N tilde. Just, I mean, easier to say, just pi inverse of Y. And yes, and so this is algebra. So XE to YE is what's known as symplectic resolution of singularities. Where so now pi inverse of E, now E is a central fiber, and so pi inverse of E is Lagrangian.
Rom, I'm a bit confused because you mix a kind of finite characteristic in
No, there's
your
no finite
example.
characteristic.
No. Here, because I have no idea what do you call algebraic symplectic manifold when characteristic is not zero.
Well, first here characteristic is zero, really, but on the other hand, it's completely algebraic notion, and you can also do it. So you just
no, I don't know, because there is some I don't know what definition you use in finite, because you have non-degeneracy condition, so a finite field, it can be a little bit. I mean, is it just standard? I can think that.
no, it's I mean okay, let's avoid characteristic 2 to
Yes.
to just be on the safe side, and then it's just linear algebra works the same. But yes, but
is it still a resolution of singularities and finite characteristic as well?
Maybe you have to exclude bad primes. But yes, in some
The
other,
characteristic should be good,
yeah, that's what I just said. Exclude bad properties.
larger than the constant number.
Maybe. Thank you. Okay, but so for now, yes, for now, for this talk, I can be received. Okay, so
Maybe okay. I don't know. You want to say that your symplectic manifold has kind of center. I mean, some Lagrangian skeleton, and well, I understand it's in the real case, but I absolutely have no idea what do you mean in finite characteristic. Even in complex case, probably you should explain. Of course,
no,
you
okay.
can.
I mean, maybe I shouldn't insist on the word skeleton because getting out of mind.
Because here there are some people who have some
Yeah, have
meaning. Yeah.
in the on their minds. But okay, so no, maybe the important feature is that we have a like GM, like C star action. So everything is algebraic here, algebraic subjective form. C star action contracting YE to the point to E, and hence, since it's just no singularities, it's proper, so hence XE to BE, and the dilating the form, and you know, T star omega T squared. So this is the main feature, but yeah. So in particular, they are. But by the way, already just existence of this structure already implies some properties of B. For example, this follows that cohomology of BE is pure. There's some old argument because you can get yeah, okay, so leave it here. And so okay, so just the last thing I want to say here is, yeah, SE can be there is a concrete choice for SE. Maybe I just mention it for completeness. So can be chosen as follows. So this is called due to Slodowy. It's called Slodowy slice. Slodowy slice. So the standard. So using Jacobson-Morozov theorem, you find a homomorphism from phi from SL2 to G. So that phi is 0, 0, 0 to E. And then there is the Kessel-to triple EHF. And then you can take SE to be E plus the centralizer of F. And everything works out beautifully. But what is more relevant to us is the following fact, which is the last thing I mentioned here, is that so YE and then XE can be obtained from the N and N tilde respectively. By Hamiltonian reduction. So maybe I explained, so assume first for simplicity that E is even, so it means that well, the corresponding homomorphism from SL2 factors through PGL2, in other words, H has only even, H has always integer eigenvalues, but it has only even eigenvalues on G. Then you can take this subgroup P minus, which is whose Lie algebra is can you still see my screen?
No, if you wrote something about the group P minus, I don't see it.
Something is not right. So I just have to
reconnect. Yeah.
Reconnect. So that I don't know why this happened. But, hopefully it will be easy to fix. Okay. Okay, so okay. Yeah, its Lie algebra is G less than or equal than 0, which means the sum of H eigenspaces with negative eigenvalues. And then E defines, so the point is that E defines a character. So G less than 0 has a character. By character, I mean just a homomorphism to abelian algebra. X goes like psi since X to EX, where this is in very linear form. And then we can take, so the claim is that XE is entailed, so this is a algebraic symplectic manifold. And then you take the Hamiltonian reduction with respect to P minus, but with that, maybe called psi E, with that character, meaning I have the moment map, so I have mu inverse of E maybe, and then divide by P. And in general, it works in the same way. In general, I mean, in a similar way, but P minus, so the algebra of P minus will not be the whole G less than 0.
Rome, I'm confused. Where is PCE in the right hand side? I thought that you make a Hamiltonian reduction not at 0, but at the character.
Yes.
But
Yes.
it's not what is written. But anyway.
Yes.
Okay.
I take the mu is the moment map. I take the pre-image of
your character. Yes.
okay. So okay. Yes.
Yeah, it's
Okay,
yeah, I understand
okay.
it's the same.
Maybe maybe I'll say it this way: of D psi E. Maybe that's
okay.
but D psi E.
Yeah, I understand. But
okay, thank you. So yeah, so the point is that G less than 0 goes to G minus 1, and it turns out that this turns out to be a symplectic vector space, and there is an additional choice. So this is going to be to some Lagrangian subspace L, which has to be chosen arbitrarily, and so L is pre-inverse. Okay, so maybe this is this detail will not be appear later, but Okay, so yeah, just this Hamiltonian reduction construction is important for many questions. For example, quantizing this varieties, I guess, as finite W algebras that people study, and having its realizations. Hamiltonian reduction is really helps to quantize it.
But in the case when it's more general symplectic resolution, and if I know how to quantize it, so this part can be skipped.
Okay. Yes, I mean, I'm not saying that this is the only method to quantize it, but this is
Yeah, okay. Okay.
Okay, so yeah, okay, there are no other questions. I can pass to like affine situation. So affine meaning loop group. Generalization. This is where our work, this is what our work is about. So now, well, if we decided to take so this BE would be generalized to what I called full E, which sounds in full. So this is a affine flag space. So now this is a homogeneous space for the loop group. So maybe we can stick to SLN as we decided to do. And then for G being SLN, we let like before we had n-dimensional vector space and we looked at flags of subspaces, and now we take, say, if we work like start working with C, but now we have this this is going to be F, and so I take now V will be F to the N, the Laurent series, and full parameterizes flags of lattices. So I have like something like L0 is contained in L1. In Ln, and well, we can in principle continue, but the condition is that Li plus N is T inverse Li. And okay, this will be for GLN, and for SLN, there is also a normalization condition. L0 has a relative dimension 0 with the standard lattice. Okay, so this is a concrete. So yeah, I should maybe write here that Li F to the N is a lattice. So Li is isomorphic to the Taylor series. Okay, and then we can take now E will be in the Lie algebra of the loop group. And we can again take full E to be the set of things, the variety of things such that.
So no nilpotency condition now.
Okay, in principle, we did have to write an nilpotency condition before, but it was just forced. If you say that E of Vi is inside Vi minus 1, it's going to be nilpotent. So if I define B that way, it will be just empty for non-important elements. So here it will be empty when okay, how do I define it? Maybe let's say it's in L. No, okay, I think it's good. Yeah, then full E is going to be empty if E is, unless E is what's called topologically nilpotent. So this means, instead of saying that eigenvalues are zero, we just say that eigenvalues are in the maximal ideal. Eigenvalues have positive, like valuation of eigenvalues, it's positive. And in other words, as a matrix, it has this e to the n tends to zero in the t-adic topology. Okay. And yeah, you see that if the matrix sends Li to Li minus 1, then clearly powers will tend to 0. It just gets smaller and smaller. All right, so and then so yeah, so in fact we want these eigenvalues to be non-zero. So if facts so if E is irregular semi-simple, then a full E is finite dimensional.
I do not see
Something against that.
I don't know. The last thing is, yeah, okay. About the matrix which goes to 0, but what do you mean by regular semi-simple?
No, I'm now about, no, okay, it's just being slow. It shows things. I don't know really what's wrong with it, but there's something okay, now all the text is out. So regular semi-simple just as an element in the abstract in G of F. In other words, the eigenvalues, they have to be this they have to have a positive valuation, but they have to be non-zero and distinct. Let's say eigenvalues in the adjoint representation have to be non-zero. Hello?
Yeah.
Okay.
Yes, okay.
Is finite dimensional, projective, but possibly int variety. So I can give like 2 examples. If G is a sawtooth, and so if E is something like, well, 0. Okay, maybe I get 3 examples. The best example is this, and then full E is just a point. So this is an analog of regular nilpotent. And the next example is it's T times that. So E is 0 T squared. And then full E is union of 2 lines, exactly like that. And if E is T0 minus T, and then full E is, it's an infinite chain of P1s. Before, like we had in SLN, we had like chain of n minus 1 P1s, but this is in a way. But this is the worst thing that can happen. So it's always like possibly has infinite union of components, but all these unions, each component is a finite dimensional projective variety. Moreover, it always has an action of a lattice. Has an action of a lattice, in this case Z. So that for E modular like of a lattice like lambda E. And lambda E is projective. So not on. So you basically each component is a projective variety, and you can only find many isomorphism classes, but they may be so.
Yeah. Sorry, Roman, I have a question. Is it always equidimensional, or is it just?
Yes, it's known to be equidimensional. Actually, it's the same proof as in the fine dimensional case, which notes here. Yes. And well, again, the geometry is quite interesting and maybe more complicated. And I will so if you do point count and trace of Frobenius, so this is related to harmonic analysis on PhD groups, and there's this famous work of like this Bao Go, for which he got the Fels medal. So, but I think there's more to explore there. So there are a few papers also I wrote on with Kazdan and Warshawski. I mean, nowhere near in terms of like strength of results, but still. So so this is kind of an ongoing project. And also they realize like the cohomology is quite interesting, and yeah, maybe I will mention a little bit what interests me, but so cohomology of E realizes representations of Daha.
When you say cohomology of something which is like infinite type, are there
Okay,
any
I mean it's
problems?
infinite dimensional, but you can take if you don't like.
No, I like the question is whether I take something. I don't know. It depends what kind of cohomology.
No, okay, it's yeah, there are ways to say it. So you can just so homology is always how to say maybe no, just homology is always finally generated over this lambda, so it's quite mild. So you can take cohomology is always finite dimension. So essentially, up to minor modifications, it's you are dealing with, you know, maybe not necessarily fine dimensional vector space, but fine dimensional module over a lattice free abelian group of finite rank, so it's not too bad. Okay, so right, and so one can ask the following question. Is
So
there...
the Daha is still corresponding to the Weyl group of the group?
Yes.
Uh-huh.
Okay, I mean, there is a lot of activity, and you know, I can so again, it would be another talk, but maybe also best not given by me. I mean, there's very interesting work by Gorsky, Oscar Kivinen, maybe I should pronounce her name, Kivinen, Gorsky, Lomkov, and also there's a work of Pablo, my collaborator, but Glosiev.
Which Gorsky?
Eugene.
Okay, so the UC Davis.
Yes. So
Thank you.
yes, so anyway, many things to say, but anyway, so question is yeah, so I should say it's not complete. Is there something like Slodowy slice? It's maybe, and so answer probably not. It's not like a theorem, but one indication is that existence of something quite like the Springer, it's quite like this Slodowy slice. Like, and let's say existence of Slodowy slice, as I mentioned, implies purity of cohomology. And so purity of cohomology is still, I mean, this is what Ngo was trying to prove, and even with his, powerful methods, he only proved something weaker. And so so purity of cohomology is still unknown, and I forget it. It's probably it's an unknown whether it's true or not. Our kind of result is a construction of something like this. It gives positive answer. A positive answer for some E, for some Springer fibers. And well, again, in a way, based on like the overall idea is not new at all, but we just show exactly how to do that. Well, maybe I should first say the keywords, namely for homogeneous. For homogeneous E, and the answer is it is based on, well, at least in some approach, it is based but related to geometry of Hitchin space, of a Hitchin space. In general, the fact that the kind of structure of Hitchin space and Hitchin irreducible system is related to Hitchin map, is related to Affine Springer fibers. That was already so this has already appeared, and this is in a way this is the key key thing that makes it work. Of course, still a lot of technical things to prove then, but it's already appeared in Ngo's work on fundamental level in maybe early 2000. Exactly. Yeah. Okay, so let's see. So going in order, I think I need to say what the homogeneous Springer fibers are, and then maybe say a few words about the construction and applications. So the point is that maybe one starting point is this, that for every I already used already mentioned this, like answering the question of what are the key geometric kind of features of that situation. So for finite dimensional story, yeah, it carries an action of the multiplicative group. Both B and SE carries that action of GM that I already advertised, but I didn't say where it comes from, it comes just from the same SL2, comes from like these diagonal matrices of C star like inside SL2, which is comes from, you know, mapping to G as before, compatible with the SL2 triple EHF that was used to construct the Slodowy slice. But there is no natural action of C star on full E in general. So E carries well a similar action only if E, you know, only for some E, and namely the idea is that we should, I mean, there is certainly nothing like Jacobson-Morozov theorem, but instead our starting point should be the loop rotation action on the loop group. Consider the action, the loop rotation action on and then by transport of structure.
Okay, what's the loop rotation in this case? Ah, thanks. Yes.
Yes.
Mhm.
You're right. So if so E is called homogeneous if the rotation action, yeah, maybe let's call this RS rotation by S. If RS of E is conjugate to something proportional to E, to lambda E. So this is like this. And then by elementary group theory, you can choose like M and D, so that RS to the M of E is proportional to, is conjugate to S to the DE. So this is called is homogeneous of slope D over M. So example, all examples are like,
right?
huh?
Conjugation is for the loop group element.
Yes.
Okay, thanks.
So it's something you can express in terms of the equality of characteristic polynomials. Characteristic polynomials of this matrix. So
You promise an example.
sorry. Huh?
You promise an example.
Yes, I promised. In fact, the examples that I already gave were both homogeneous, but I now have again the same problem. It seems that my device got disconnected, and this is unpleasant. sorry. I don't know why it's doing that. Okay, so so maybe I need to connect it to the charger. Okay, fine. Okay, sorry. So yes, and the example was that if I take S to be like constant, regular semi-simple matrix, and then E is TS, this is obviously slope 1. And if I take something like once on the diagonal, and then T in the upper right corner, so it's behind. Then this is going to be slope 1 over n. Yeah, it's not happening before. Okay. So the idea is that we would be like.
So S belongs to what?
It's a regular semi-simple matrix S, maybe you can think of it.
Rom, I thought that S was a number. S was an element of GM.
Okay, that's a good point. I'm sorry. So yeah, it's a complex of notation. So let's change it because I'm used to X. Okay, this is better. So lambda I are like in the small field and constant. So this is a kind of example for SL2. This is a kind of example I gave before. Yeah, this is a okay. And then I mean, without further ado, I can just say kind of the main theorem. So main construction. It's an algebraic symplectic. Okay, in general, it's because of this infinitely many components, so it's int variety. ME. Now it's okay, let me finish the sentence. So it's an algebraic symplectic variety, ME, where full E is a Lagrangian subvariety.
No, it's better to wait until you reconnect, because it's kind of difficult to get.
Maybe I can, let me maybe stop broadcasting for just half a minute, and then I'll relocate to another place in the house, and maybe it will be a connection will be better, and this problem solved.
Okay.
Okay, so let me do that, and then can I switch off the. All right, so I have relocated. Both things on the bottom. Even worse. Yeah, it says that it's connecting. Okay, I'll try to do it again. Okay, so it should be back now. Okay, so we are back. Sorry about that interruption. Yeah, so construct an algebraic symplectic invariety, which is where full E is a Lagrangian. Lagrangian. But in contrast with the finite dimensional situation, this is not a symplectic resolution of singularities. It's rather an integrable system. An integrable system. Not not a symplectic resolution. And so, okay, maybe I'll just give a quick construction in one example. Actually, can you hear me? Hello?
Yes, 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 yes.
Yes, we
Okay,
can
then
hear
I
you.
see, yeah, you also see the screen. So construction for E equal to just Tx as before. And in a way, this is my favorite case for the reasons that I may explain in a few minutes. And then we just take, take P minus to be the congruent subgroup in the negative G of negative loops. So congruent subgroup. First congruent subgroup. So were those so Lie of P minus is T inverse G of T inverse. And we have psi E such that d psi E takes X to, well, a residue dt over T. It's the usual like pairing. And then we take T star affine flags. Okay, so and yeah, there is some a story which is more kind of least theoretic nature. So homogeneous elements can be classified. For example, let me just quote one thing. So just in the direction of the more general story that I don't want to describe in detail. Classified, and then for each E, we construct P minus sort of E with psi E, which is character of P minus of E. So one fact is that the slope that appeared before is always D over M, where M is a regular number. And so regular number, so this is some story about, I think due to Springer originally. It means that it's an order of a regular element of W in W, where W is regular, which means it has an eigenvalue, an eigenvector, which is a regular element. It has an eigenvector, which is a regular element in Cartan. Okay. So, okay, this is some non-trivial, and this is actually related to then the study of Z mod M gradings on the finite dimensional algebra. So some rather classical chapter. Classical, okay, very questions.
Not on Z mod N, but on G. Probably.
Oh yes, easily. Because on G mod M is the way it takes values.
Yeah. Okay, but it's sort of Hitchin is not visible here. And
Okay,
actually...
okay. So that's maybe something I still need to mention. And because yeah, this relation to Hitchin space, it's also kind of gives more information, another perspective from the symplectic thing. In particular, it allows to define also like this M E will be so remark, or the next point is that this ME can be realized for those who are kind of familiar with the terminology as M Dolboy in some Hitchin-like story, and then also have M Deram and M Betty. And this gives some interesting information. So in particular, well, maybe I'm running a little bit ahead of myself, but I just want to say that in this context, we don't prove the full package of non-abelian Horst theory, because this, again, as I will say in a second, it will involve some connections with irregular singularities where the foundations are harder to establish and it's not clear which facts are true. But at least we show that we construct a family degenerating M Deram to M Dolbois, and show that, for example, it's kind of have the same cohomology.
So, Rom, when you say M Deram, M Dolbois, you mean moduli spaces, not stacks?
Yeah. In this case, you see, I mean, This Hamiltonian reduction is in a way because of this psi, we kind of land in some open locus where there are no stabilizers. Maybe that's
Also,
so-
concerning, you said that it's irregular, Hitchin, this cohomology, are they still pure in the irregular case?
You know, I think so, but let me. No, I think it's. I think it is true. For example, you know, homology is after all homology of this Springer fibers, and for those particular Springer fibers, maybe I should have mentioned. I think purity was already known by Garetsky, Kotovitz, and McPherson, but maybe I can, you know.
So your underlying curve,
give you a fuller report on this question later because
but your underlying curve is a projective line, yeah.
Yes. Okay. So maybe I should go to this. Yes, and then we kind of almost just to finish this almost show the RAM is embedded as analytic manifold. Okay, the point is that this show it kind of modular some, you know, references in Stokes theory, because it's just because the as I said, it's kind of has to do with irregular connections, so it has to involve irregular Riemann-Hilbert correspondence, and then it turns out that people, you know.
No, but I think there are some.
No, there are, but you know, so people who like to study Stokes theory, some of them don't.
Probably
much general reductive group. Okay, if as you
okay, probably
advise me, you would stick to SLN, maybe it would be, maybe we kind of have the reference. Anyway, it's kind of
okay. So it's some minor thing which
minor thing. Yes. Technically, we it's a conjecture, but yeah, I think this Betty is quite interesting too. Maybe I can give an example. Just okay, I should say what it is about, but I really like this kind of geometric thing. So example again, if E is x tx as before, and then so for SL2 for G is equal to SL2, it's this chain of lines, and in general it has, you know, rather rich geometry. So say for SL3 it will have two types of components. So there is always a component two types of components for SL3. So there's this G mod B, which is there is always such a component, and also there is this X, which maps to a blow up of P2 at 3 points, namely the eigenvalues of X with fibers P1. So it's still not. But again, this may be misleading because in general they're very singular, but SL2, SL3, they're smooth. But then Betty, it will be something like this. It will be a covering. So we take GS, so general, a generic like semi-simple orbit. And then we intersect it with B plus B minus. And then for so this B plus B minus come from Stokes data. So these are matrices in a given conjugacy class with a Gauss decomposition. and then, you know,
So you have what? You probably then you should have just one irregular point. Otherwise,
exactly.
Yeah.
So and then they have so this tilde means some sort of, because this was an infinite thing, and then you have universal covering, which means that you know, this projects to, since it's in B plus B minus, so it projects to Cartan, and then you have universal covering. And yeah, okay, so yeah, so I should maybe say finally what we are doing. Yeah, as you said, so the point is that this T star flag actually can be interpreted. I mean, the Hitchin space. So recall that the Hitchin space is the cotangent space to band G, and band G can be. Maybe I should start with the following point, that if I take band of P1, then this is a fine Grossmanian, just a space of lattices. Modular, well, a G of C of T inverse, right? So this is like the standard thing that you have projective line, and then you glue your, I mean, you have a G bundle, and you can trivialize it away from a 0, and then you get a point. Local data near 0 gives you a point in the Affine Grossmanian, and then modding out by these trivializations, you get this description, and then you can kind of modify this. So bond. So for example, yeah, you just basically add stuff to it. So find flag variety mod G of C of T inverse. It's the same as E is like G bundle on P1 with a flag at 0, and flags modular the congruent subgroup this is just the same thing, but plus trivialization plus frame at infinity, basis at the phi by at infinity. So here we, and of course, when we do Hamiltonian reduction to the cotangent bundle, it's the same as cotangent bundle to the stack. But because of this trick, because we right, and I think thinking about this, maybe I should first mention the non-twisted version, right? So the T star of flags mod P minus. On the one hand, it would be T star of flags. Now Hamiltonian reduction by P minus without, I mean, with 0 moment value. So this would be just in the Higgs field. So that would be E phi. Well, this is like a G bundle and P. So a G is a G bundle on P1 plus flag and trivialization. At infinity, and phi would be in H0 of at E times KP1, and then it is allowed to have like 0 poles at 0 and infinity. where a residue at 0 preserves the flag, and residue at infinity preserves the basis. But now, since we introduced this character, then technically it's, we have to think about the quotient, by the kernel of this character. So this will translate into, like, in our case, E will have, at 0 it will be as before, but we'll have an order 2 pole at infinity, so that
Rom, not E, probably phi.
yeah, thank you. Yes, phi will have order 2 pole at infinity, so that the polar part is diagonal in that basis. Is diagonal in the basis and has a fixed generic eigenvalues. Has fixed eigenvalues determined by S. Maybe in the previous notations, like number 1. And then you can imagine how this is, if this is M-Dalbois, then you can imagine how M-Betty looks. Okay, so
no, I cannot until I see M-Dram. How can I imagine?
well, if you know M-Dalbois, then I guess it's more algorithmic. So yes, a procedure to get M-Dram. So M-Dram would be,
yeah, okay, yeah, I get it.
Bundles with connection.
Yeah, because you're on P1, it just, just connections with connection matrices with all these properties.
Exactly, yes, exactly. So we have singularity. We have regular singularity.
One regular, one irregular with in this case order 2 pole.
Exactly.
Yeah.
So this is rather standard. Again, we are considering in the paper, we're considering more general situations, but this is, I think, good enough illustration. So yeah, okay. So maybe it would be a natural place to stop. I can just say, kind of advertise some other constructions involving this Springer. I mean, this particular Springer from him. Okay, maybe I'll just say about the next paper. So this is some equivalences inspired by local geometric Lagrangians, inspired or local geometric Lagrangians. We prove the following theorem that for, again, E is Sx. I'll give the statement without fully explaining the terms, but
so S equal S mean T or what?
Yeah. That microlocal sheaves on ME supported on full E is equivalent to the category of modules of a small quantum group at the root of unity. Although technically, okay, graded by the lattice. Although technically it's not, that, but it's causal dual to that. Principal block. In any case, so there is some category of like some geometric game you can play on this MC, and it spits out a category that's representation theoretic inference. And so application to a problem that, you know, maybe going back to Igor Frankl in the 90s and then worked on by his students and postdocs. And so if I take the center of a small quantum group, write it in log. So it receives a map from cohomology, actually injective map from cohomology of E. So conjecturally an isomorphism, and can be constructed by other methods with the same myself and same Pablo, but also some in this room. And okay, I think we're making progress also. Taking the isomorphism statement in some cases, but at least this is what I want to mention here. Okay, so maybe this is a good place to stop. And there are other questions.
Yeah, thank you very much. This last result which you mentioned, it resembles, does it? Maybe not. No, it's. I wanted to say that it resembles the Riemann-Hilbert correspondence, but then I'm not sure because both sides looks topological.
No, okay. So in fact, the way I was led to this was so originally there was a conjecture which was more like motivated by homological mirror symmetry rather than, or maybe it was by both. I was trying to connect them better. Namely, it was saying that the right-hand side in some form. I mean, there are also things I'm not describing. There's also some coherent realization. So it can be also related to some TB-Koch. But in any case, so the right-hand side, it should be the same as the Fukaya category of M Betty. So that's what
strange because the left-hand side looks as a Fukaya category because it's micro.
Yeah, but the connection between the left-hand sides is now maybe similar things are in the literature, right? So people, so microlocal sheaves on the Dolbeau space should be the same as Fukaya category of the Betty space, but just for me, it's kind of easier to work with. You know, easy to understand the definition of microlocal sheaves and Fukaya category. And so so this is kind of the approximation to this conjecture that. So okay, maybe I should say that should give this B-side generalization. So it's DB-Koch of N tilde, but now for the dual group.
So it's again not reflected. Probably something is wrong with the bottom of your pages.
No, actually now it is reflected because I started writing in a different place. Actually now.
Okay. So everything is normal.
Maybe I'll write it this way. So I'll start. It's equal to some sort of C coherent, and then I write here C coherent. It's DB-Koch G check of N tilde. Now G check, and well supported on the 0 fiber. And the equivalence of this to the quantum group, this is kind of known, but and so this is basically the manifestation of this idea that I had that M Betty is mirror dual. In a way, maybe it can be interpreted as some sort of mirror duality between Betty spaces on the two sides.
A mirror dual to what? To another M Betty? It depends because
I think well that was only, I think this It's not how I was thinking about it, but I think McBreen lady explained to me that this is how it should be interpreted. There's a little bit of this discussion in the paper too. But okay, so explaining details will take time, but this is,
some details are in your paper, so I hope that you explain them. but in the end, you should read them.
Okay, the way I was thinking about originally is that this particular space, that this GS cap B plus B minus is a mirror UT star D check, maybe check. But if you sort of think about it in the right way, then you can tie both sides to a version of the Betti space. But yeah, maybe we can.
Yeah, you see, the thing which kind of a bit confuses me in all this business is that both sides of mirror symmetry, they are kind of complex. They are not real, not C infinity.
No, this is okay. I mean, the it's just this hyperkähler context. So yeah, when we in the Foucault category, this will be actually real Lagrangians. So in the here,
but for that you need to rotate complex structure,
yeah.
and you said that you have some problems with full twistor space. Yeah.
Yes, that's right. No, I mean, technically, I have nothing to report on this original form, the conjecture. Maybe other people.
No. But even at the level of conjectures.
No, but I mean, it's. I don't know if one should expect. I mean, there should be something like. I mean, we construct a part of the twistor space, like removing infinity. But, whether one literally should expect the hyperkähler structure, that's not clear to me. I mean, maybe I heard from some physicists that Gayotto that there are reasons to expect that there's some hyperkähler structure given by like a divergent series, but maybe it exists in some analytic.
Probably
maybe it converges in some analytic neighborhood of our special phi.
No. I mean,
the most optimistic thing I hope for is that it exists well defined.
No, since you kind of you already mentioned some periodic stuff. So their construction of the hyperkähler structure on the Hitchin space, it gives you a non-Archimedean hyperkähler. So they have a parameter in the theory which is it's a radius. Like they're physicists, so they start with some four-dimensional theory on the product of R3 and the circle has a radius, and so whatever they construct, it's a series in one over this radius. So it's non-Archimedean parameter like UT, but probably of different nature. And so the series they converge in non-Archimedean sense. Probably they do not speak in this language, but that's so then probably
this sounds very interesting. And so they are, I mean, to understand this,
they means Gayotto, Moore, and Neitsky, probably what he meant. They wrote a paper with an approach to the construction of hyperkähler metric on the Hitchin space. They did not consider irregular, but I mean, I don't think it's a big deal. They considered maximal regular singularities, but for an arbitrary curve, not only for CP1, with prescribed, I think, semi-simple residues of the Higgs field.
Mhm.
And so the construction, it's pretty, I mean, it's uses as our wall crossing business with Maxim. It's they kind of glue semi-flat pieces, but they cannot prove in the end. They write some integral equation like it's kind of sort of thermodynamical Bethe-Ansatz type equation, but they cannot prove that the iterative procedure in their paper for solutions that it converges. So it's because it's they give an answer in terms of sums over trees, and you know that's a problem. Like if the number of trees grows super exponentially, then there might be a problem with convergence, like in physics. So anyway, so probably there is a non-Archimedean convergence, and for the purposes of mirror symmetry, it's often sufficient because, for example, this SYZ story, you have an equivalence of some Fukaya with some dB Koch on the non-Archimedean space. It's kind of maybe it's sufficient, but what you said about this microlocal, yeah, it should be some. Let's see. It's analogous if indeed I think about this affine Springer fiber as a Lagrangian skeleton, whatever it means. So you have microlocal shifts supported on the skeleton, yeah?
Yes.
Now, if you so then it's a local kind of in a different setup because kind of too many infinities here, but in conventional story you have a singular Lagrangian and a complex symplectic manifold, and these microlocal shifts, they correspond to the local Fukaya category, which means that you have just a Liouville neighborhood and you just do the Fukaya business. So this is your left-hand side. On the right-hand side, you say that it's dB Koch.
You're right.
For me, it would be easier to go to the RAM story, which means not to compare with dB Koch, but first to compare with holonomic DQ modules on either on ME, maybe on even on the whole. No, probably.
Yeah. That's possible. That's basically.
Yeah. Like holonomic.
That's basically what we are working with in any case.
Yeah. Supported on this Lagrangian skeleton. And this is sort of, it's a very algebraic thing. So then for this you can prove, maybe, I don't know, that indeed it's equivalent to whatever dB Koch on the.
But how to go from that to Fukaya category?
Where on the right hand side? Okay, no, it's the question is how to go to MBT. Because Fukaya, you already your left hand side. Sorry, for me the left hand side it's a local Fukaya category, which means that you ignore all pseudo-holomorphic disks with a boundary on your Lagrangian skeleton, probably, but maybe you should not. Then it becomes even more interesting, because ME is really not small. It's kind of a big symplectic manifold, complex symplectic manifold containing your Lagrangian skeleton, and theoretically there might be some instanton corrections, some like you start. I'm not sure. Maybe it's a very interesting story. Because when you start with just a complex Lagrangian, maybe singular inside of a complex symplectic, when you take a small neighborhood of your Lagrangian, then no instant-on corrections, but there might be big ones, yeah, which mean that they are disks in the rotated complex structure, holomorphic in the rotated complex, with a boundary on your Lagrangian, and it deforms the category. So if you take a small neighborhood, it's indeed microlocal shifts just sitting on your, in your case, on this FL, on the Springer fiber. But maybe in honest category, it's a deformation of this one. Okay. Anyway, it's kind of indeed it's a long story. Maybe we
Okay,
should...
thank you very much for these comments and for listening.
Yeah, okay. Maybe there are more questions because I kind of occupied whole Q&A.
I do have a question. Earlier you mentioned about the Yindel variety of a symplectic variety. So what does that mean? Each piece, when you take the direct limits, should be a symplectic, or...
So you worry about this infinitely many components?
That's right. Well, when you do the Yindel, it's just a variety is the Yindel, you have some sort of symplectic structure.
Yeah, no, I mean, in
on
general,
each piece, you want to have a symplectic structure when you take the Yindel.
So yeah, so I think it will be only ME is a variety only, technically a variety only if E is elliptic, in which case, yeah, it's difficult. It doesn't arise, and in general, it's an IND variety. It's also some sort of infinite.
It's only a Yindel variety, but the symplectic structure is not necessarily a Yindel symplectic structure.
Anyway, so
even earlier, I guess.
Yeah, just where I say EME, I think there was, yes, I think there was this little IND in parentheses. I mean,
yeah, I was curious because for the embedding, there could be embeddings of symplectic variety into another one, but
yeah.
Okay, great. Now, Roma, can you send a copy of your notes?
Yes, I will.
Yeah.
Okay, thank you very much. Again.
Okay, thank you. And so, okay, we can discuss other stuff.